You know how sometimes you get like a diagram for something new? Maybe setting up an app or, I don't know, even putting furniture together.
Oh, yeah, the instructions.
Right. And you realize that understanding those little symbols, the arrows, the plus signs, whatever they are,
Hmm.
that's the real key. Grasping those basics just unlocks the whole thing.
Absolutely. It's the foundation.
Well, today we're doing a deep dive into something similar, but for Python code, operators.
Ah, the action words.
Exactly. Think of them like the fundamental verbs of Python. These little symbols and keywords, they seem small, but they're what actually make your code do things.
Perform calculations, make decisions.
All of it. And getting a handle on them, I think it's a shortcut to really understanding Python at its core.
It really is. You can define all the data you want, but without operators, that data just sits there. It's static.
Right.
Operators are what bring it to life. They compute, they compare, they assign values, they handle logic.
Yeah.
They're basically the essential toolkit for turning information into a program that actually works.
So our goal today, our mission, is to really unpack these. We'll go through Python's operators, group them by what they do, and look at why they matter in practice.
Yeah, we want to give you a clear map, so when you look at Python code, you can see past the syntax and understand the actual operations happening.
From simple math to complex logic. By the end, you should be able to glance at some code and just get what it's trying to achieve.
Let's dive in.
Okay, let's start with maybe the most familiar ones. Arithmetic operators.
Mm-hmm.
These feel pretty intuitive, right? Like Python has a built-in calculator.
Definitely the most straightforward place to begin. They're for doing math.
So we've got plus for adding, for subtracting, for multiplying. Pretty standard stuff.
And for exponentiation, raising to a power, crucial for lots of calculations.
But division. Python does something a bit interesting there, doesn't it?
It does, and it's important. These operators are the workhorses for any kind of numerical task, really. Data processing, science, simple counting.
Okay, so lay out the division ones for us.
Right. So you have the standard for division. The key thing here, it always gives you back a float, a number with a decimal point, potentially.
If it divides perfectly, like 10 divided by 2.
Yep, 10-2 will give you 5.0. Always a float.
Okay.
Then you have A, that's floor division. This one gives you an integer. It basically chops off anything after the decimal point.
So 17.5 would be...
3, it just discards the 0.4.
Gotcha. And there's one more, right? The percent sign?
That's percent, the modulus operator. It gives you the remainder of a division. So 17%, 5 would give you 2, because 5 goes into 17 3 times with 2 left over.
Okay, that distinction between cal and wittable, the float versus the integer, why have both? Seems like a place people could get tripped up.
It's a really good question. And yeah, beginners often mix them up. But it's about giving you control over the type of result you get. Precision matters.
So when would you absolutely need one over the other?
Well, think about money. You usually want exact fractions, right? So you'd probably use wittable, the float division.
Makes sense.
But what if you're calculating how many full boxes you can pack with, say, 100 items, and each box holds 12?
You don't care about the fraction of a box left over.
Exactly. You want the whole number of boxes. So 112 gives you 8. That's floor division. Using might give you 8.333, which isn't directly helpful there, and could even introduce tiny floating point errors if you're not careful.
Right, so it prevents those weird little bugs. Control over the result type.
Okay, that makes sense. So once you've done your math, you need to store the answer somewhere, usually. Or maybe update a running total.
Exactly. You need to assign that value.
Which brings us neatly to assignment operators. These are how Python, remembers things, right? How you give a value a name.
Spot on. Their main job is binding a value to a variable name. The most basic one everyone knows is just value on the right gets assigned to the variable on the left. Simple.
But Python has those handy shortcuts, the compound ones.
Ah, yes, the compound assignment operators. They're fantastic. They combine an arithmetic operation with the assignment.
So instead of x plus 5, you just write x plus equals 5. Much cleaner.
And there's one for most of the arithmetic operations.
Pretty much all the main ones. You've got plus, eventress, even, percent. They cover the bases.
I really like those. X plus E1 just feels so much more direct for incrementing something than writing out x plus 1.
It really does. And you touched on a key point there, readability and expressiveness.
How so?
Well, x plus 1 works, obviously, but x plus equals 1 explicitly states your intent. You're saying take the current value of x and add 1 to it. It's clearer, especially in more complex lines or inside loops where you're maybe summing things up.
So it's kind of a signal to someone reading the code later.
Exactly. It's just cleaner, easier to grasp at a glance. A good habit to get into for maintainable code.
Okay, so we can do math, we can store the results, but programs need to make decisions, react to different situations,
They absolutely do. They're not just calculators.
which leads us to comparison operators. This is how Python asks questions, isn't it? Like, is this value bigger than that one, or are these two things the same?
Precisely. Their whole purpose is to compare two values. And the crucial thing is they always give you back a Boolean answer.
True or false?
Always true or false. They are the absolute bedrock of controlling the flow of your program, making decisions.
So what's in this toolkit?
You have, for checking if two things are equal in value, note the double equals.
Yes. Very important distinction coming up.
Definitely. Then, for not equal to, you've got very fit, and for greater than or equal to, and less than or equal to, standard comparisons.
Okay, let's hit that versus a point again. It's such a common stumbling block.
It really is. Countless hours of debugging have been spent on this one mistake.
So int is asking.
Asks the question, are these two values equivalent? It compares them and gives you back true or false.
It
Is the assignment operator we just talked about. It's a command.
Yeah.
Make the variable on the left, hold the value on the right. It doesn't ask, it tells.
Asking versus telling. Got it. Missing those up will definitely break your code.
Oh, absolutely. Syntax errors or just plain wrong logic.
No.
And thinking bigger picture, these comparison operators, they're the heart of any if statement, any while loop. Anytime your code needs to choose a path based on data.
Like checking a password.
Perfect example, if entered password equals correct password, that ITSE's doing the critical work. Or checking if a sensor reading is a danger threshold, they turn your data into decisions.
Okay, so we can ask one question. But what if a decision depends on multiple things being true? Or maybe just one of several things?
Good point, like, is the temperature below freezing and is it snowing?
Or do I get free shipping if my order total is over $50 or if I have a Prime membership?
Exactly. That's where logical operators come into play. They let you combine or modify those true-false results from comparisons.
Like conjunctions in English.
And
Or not.
precisely, Python uses those exact words, and, or, and not,
How they work.
and requires both conditions. It connects to be true for the whole thing to be true. If even one is false, the result is false.
Makes sense. Both must be true.
Or is more lenient. It just needs at least one of the conditions to be true for the whole expression to be true. It's only false if all conditions are false.
Okay, one or the other, or both.
And not as simple. It just flips the Boolean value. Not true becomes false and not false becomes true. It inverts the truth.
Those real-world examples really help. Like, for a login, you might need usernames correct and password discorrect. Both have to be true.
Spot on. Or maybe access is granted if user is admin or user has special permission. Just one needs to be true.
Very intuitive.
And there's a clever optimization here called short-circuiting.
Ooh, what's that?
With and, if Python evaluates the first condition and it's false, it knows the whole and expression must be false, right?
Right, because n needs everything to be true.
So Python doesn't even bother checking the second condition. It saves computation time.
Ah, and/or does something similar.
Yep. If the first part of an OR is true, the whole thing must be true, so Python skips the rest.
That's not just faster. You could use that strategically, couldn't you?
Absolutely. Imagine you want to check if a list has elements, and if the first element is, say, apple. You could write if mylist and mylist0 equals apple. If mylist is empty, the first part is false, and Python short circuits, never even trying to access mylist0, which would have caused an error on an empty list.
Clever. So it helps write safer, more robust code, too.
Definitely. Understanding short circuiting is key for both efficiency and correctness.
Okay, this next one. It feels a bit more subtle. We talked about comparing values. But Python has operators for comparing identity. What's that about?
Yes, the identity operators is and is not. This is a crucial distinction. They don't check if the values are the same. They check if two variables refer to the exact same object in the computer's memory.
Whoa, so not just twins, but the same actual person.
That's a great analogy.
Yeah.
Asks if two things look the same, have the same values. It asks if they're the very same thing, the same object stored in the same memory location.
So A12 and B12, A equals B would be.
True. Their values are the same.
But A is B would be.
False. Python, by default, created two separate list objects in memory, even though they contain the same values.
Okay, but why would I care if they're the exact same object versus just having the same value?
It matters hugely with mutable objects, things that can be changed, like lists or dictionaries.
How so?
Well, if you do lista 1, 2, and then listb, lista. Now, lista is Lisper will be true.
because listB is just another name pointing to the same list object.
Exactly. And here's the kicker. If you then change listB, like listB.append3, what happens to lista?
Uh-oh. Since they're the same object, lista changes too.
Precisely. It will also become 1, 2, 3. This can be a major source of bugs if you're not aware that two variables are tied to the same underlying object. Using is helps you understand these relationships and avoid accidentally modifying data you didn't intend to.
Wow, okay. That's a really important concept for avoiding side effects. Understanding is versus sbig is key for mutable types.
Absolutely critical.
All right, moving to something maybe a bit more commonly used day-to-day, especially with data collections. Membership operators.
Yes. In and not in. Super useful.
These basically ask, is this thing inside this other thing, right?
Exactly that. They test if a value exists within a sequence. That sequence could be a string, a list, a tuple, the keys of a dictionary.
So in gives you true if it finds it.
Correct. And not in gives you true if it doesn't find it. Simple as that.
It feels very natural, like checking if Apple is in my shopping list, or if a specific character is in a string.
It makes that kind of check incredibly readable and concise.
Oh.
Way better than writing a loop yourself just to see if something's present.
Is there anything more to them? They seem straightforward.
Their simplicity is their strength, but one interesting performance point: how fast in works depends on the type of sequence. Checking if an item is in a list requires Python to potentially look at every single item one by one. So for a huge list, that can be slow.
Okay, linear search.
Right. But checking if an item is in a set is incredibly fast, almost instantaneous, even for millions of items. Sets are optimized for this kind of check using hash tables internally.
Ah, so knowing that difference can help you write much faster code if you're doing a lot of membership tests. Choose a set over a list sometimes.
Exactly. It's a great example of how understanding the tools lets you make smart choices for performance. In and not in are your friendly neighborhood search party.
Okay, we've covered a lot of ground. For our final category, let's get really low level. Bitwise operators. These sound a bit intimidating.
They can seem that way because they operate at a level most Python programmers don't usually need to worry about. They work directly on the individual bits, the ones and duals that make up integers.
So we're leaving behind the nice abstractions of numbers and manipulating the raw binary.
Pretty much. You're treating numbers as sequences of bits. This is super powerful for certain specific tasks, though.
Like what? Where would you actually use these?
Think low-level stuff. Network programming, where data packets often encode information in specific bits, maybe graphics or image processing. Cryptography relies heavily on bit manipulation, sometimes optimizing very specific, performance-critical algorithms.
So not your everyday web app development tool.
Generally not, but good to know they exist. The operators are, and for bitwise A and D, for bitwise or R, for bitwise XOR, exclusive OR, for bitwise not, and for left shift and right shift.
Okay, the AND, or not sound familiar from logical operators, but bitwise means they work bit by bit.
Exactly, and compares the bits in the same position in two numbers. If both bits are 1, the result bit is 1, otherwise it's 0.
Can you give a quick example?
Sure. The number 5 in binary is 101. The number 3 is 011. If you do 5 and 3, first bits, leftmost, 1 and 0, 0. Middle bits, 0 and 1 is 0. Rightmost bits, 1 and 1 is 1. So 5 and 3 gives you 0, 0, 1, which is the number 1.
Whoa. Okay, and the shift operators?
They literally shift all the bits in a number to the left or right. Shifts left, filling the right end with zeros. This is actually a very fast way to multiply by powers of 2.
So by 1 is like by 2.
Exactly, and by 2 is like by 4.
Yeah.
Similarly, shifts right often used for dividing by powers of 2 efficiently.
Fascinating. So, while maybe not common, they provide really fine-grained control and potential speed boosts for specific problems.
That's the essence of it. They're powerful tools for when you absolutely need to work at the binary level. Python gives you that capability.
What a tour. Seriously.
Yeah.
From basic math with arithmetic operators to storing values with assignment.
Making decisions with comparisons, combining logic,
Checking identity with is, seeing if something's in a collection.
and right down to flipping individual bits, it really covers a huge range of operations.
These little symbols really are the engine of Python, aren't they? The verbs, the conjunctions, everything that makes the code act.
Beautifully put. And understanding them, really understanding what each one does and why it exists, it just elevates your comprehension of Python code immensely.
It's not just about knowing the syntax.
Not at all. It's about grasping the logic of how Python processes information and executes instructions. That knowledge helps you debug faster, write cleaner code, choose the right tools, and ultimately build better programs.
So maybe a final thought for everyone listening. Next time you're looking at some Python code, don't just read it like text.
Yeah, try to read the operators themselves.
Ask yourself, what's this line doing? Is it math? Assignment? Is it asking a question? Combining conditions?
Is it checking if these are the same object? Or even working with bits?
You might find you gain a whole new layer of understanding just by focusing on those powerful little symbols. Try it on a snippet of your own code. See what you notice.
It really can deepen your insight.